Hello, and welcome to Algebra 2 with Mr. Clausen. Today, we are going to discuss the cosine function. Specifically, I want to look at the unit circle of the cosine function and how the unit circle relates to the cosine function a little bit differently than the sine function. We'll look at how to write a cosine function based on a graph, and then how to determine the exact radian values based on a fixed cosine value, and then look at sketching cosine functions at the end of this given video. So with that said, what I want to point out here is that when we look at a cosine function, remember that x values of a unit circle relate to the cosine of theta. So if you look here, instead of starting at the origin and going up, down, like you would with a sine function, cosine functions are a little different. They have this pi over 2 shift over. And so what that allows you to do is that you'll see that this red part of this unit circle corresponds with the very first part of the cosine function, followed by the green part, comes back up on the yellow part, and ends on the blue part. And so the first thing that you should notice is that the cosine function starts at the maximum point of the graph. It starts at x equals 1. And when the theta value is equal to 0, when theta is equal to 0 or 0 pi, all right, x is equal to 1 and y is equal to 0. All right, so this distance here, delta x at 0 degrees, is what represents the initial point of this graph. And so if we go to pi over 2, we see that 0 is the x value here and the y value is 1. So for cosine of pi over 2, x should equal 0, which we see represented here. When we have cosine of pi, that should equal -1 and represent the minimum point. As we come back to 3 pi over 2, we'll hit 0 again. And then once we finally get to 2 pi, we'll end up at 1 again, and then the function will start over. And so you get these kind of U-shaped functions, and the twist that is associated with like a sine function is it's exactly the same shape as a sine function. It's just you have this shift and you get this general shape instead of the sine function shape, which starts at the origin. So with that in mind, one of the things that I want you to be able to do with a cosine function is I want you to be able to go and write them out just like you normally would. So if you have y equals a cosine of b theta, all right, b being the number of cycles and a being the amplitude. And if we look at these values and we look at a given function like this, the first thing I'm going to do is I'm going to see, all right, if I go from maximum to maximum, and maximum to maximum, and maximum to maximum, I can see that I have 1 cycle, 2 cycle, 3 cycle. And so from this, I can count there are 3 cycles, so my b value is equal to 3. Now, if I could see very clearly that 1 cycle equaled pi over 2, I would plug that into the general equation where, you know, you have b equals to 2 pi over the period. But it was pretty simple to just look at the maximum since it starts at a maximum and see that the 4th maximum is at 2 pi. So that means there are 3 complete cycles. So b is equal to 3. And I also see that the amplitude of this, or the maximum, is 1 and the minimum is -1. So I see that the amplitude is equal to 1. So I can create a function from this pretty easily. I can say that y is equal to the cosine of 3 theta. All right. And so now what the second half of the question asks in this particular instance is determine all the points in radians when the following cosine function is equal to 0 between 0 and 2 pi. All right. And now if we look at the previous example, if you wanted to know where cosine of theta equaled 0, we see that this would occur at pi over 2 and 3 pi over 2. Those are the two cosine values in radians where the cosine function is equal to 0, which we can clearly see on our unit circle here. And so what I want to go back and look at here is that we can still use that information even though it doesn't apply directly to this given state, because what you should know is that if one cosine function, like if cosine of theta has two zeros from 0 to 2 pi, well, remember that this b value, this accelerator value, tells you how many cycles there are between 0 and 2 pi. So if you have 3 complete cycles between 0 to 2 pi instead of 1 cycle between 0 to 2 pi, you should expect a total of 6 zeros. And if we go across here and we look at this, we can very clearly see that there are 6 zeros here. And we want to find what these zeros are. They don't come out in exact places where we can exactly see them. So we're going to go and look at this and try to figure out what these zeros are. And the trick I'm going to tell you to use here is, let's look at this and go, all right, this is our unit circle, all right? And we have this point up here, this point up here. These are the 2 points on a unit circle when cosine is equal to 0, okay? And so if we draw the unit circle here, all right, in all of its perfection, all right, at this point, and we go y equals cosine of theta at these given points, or I should say x equals cosine of theta. These 2 points are when cosine of theta equal 0, just normal cosine of theta. And these theta values are pi over 2 and 3 pi over 2. All right, but that's only the first time you go around the circle. So remember, since we have 3 complete cycles, what we want to do is we want to find all the possible values of a normal cosine of theta that would be represented if we kept going around the circle over and over again. All right, so this only represents the first cycle of the unit circle. So if we were to find this position and add 360 degrees or 2 pi, we can identify this as either pi over 2, and then the next time that we hit it, if we keep racing around the racetrack, the next point would be 2 pi plus pi over 2, which if we simplify that out would be 5 pi over 2. So then the next time that we hit 0 on the unit circle is at 5 pi over 2. And then if we go down here, this is 3 pi over 2. But if we want to know when we hit that the second lap around the track, we would go 3 pi over 2 plus 2 pi is equal to 7 pi over 2. 7 pi over 2. This is our second cycle or second lap around the unit circle. And then if we go for a third lap, we add 2 pi to 5 pi over 2 and see that this equals 9 pi over 2. So then we have 9 pi over 2 and add 2 pi to 7 pi over 2, and we'd have 11 pi over 2. And this would be the theta values representing our third lap or our third cycle around the unit circle. So with this in mind, you might be like, well, why are we going so far into this? Well, the reason that we're going so far into this is we need to figure out when we hit the 0 value on the unit circle the first 6 times, because there's 6 times that it crosses here. And there's 6 times because there's 2 times every time you go around the unit circle that cosine of theta equals 0. So if we have cosine of theta, and we can cross the 0 twice from 0 to 2 pi in cosine of theta, cosine of 3 theta is going to triple that number, and so we'll have those 6 zeros like we mentioned before. So how do we figure out what these specific radian values are? Well, what you do is that you take these laps that we ran and we go, all right, we need to figure out when 3 theta, the value being represented by our identified cosine function that this wave represents, and we need to figure out when 3 theta equals pi over 2. So we divide both sides by 3, and we see that when theta is equal to pi over 6, what we can do is we can plug this into our original equation and replicate this spot on the unit circle. So if we say y is equal to the cosine of pi over 6 times 3, what you will get is the cosine of pi over 2, right, once it's simplified out, and this will equal your first 0. So this given location right here is actually pi over 6. But the reason that this produces a 0 value on the cosine function is because of the accelerating b term, the number of cycles. And so if this is pi over 6, what we just have to do is keep going through the rest of these and figure out what they are. So the first 0 that we've identified here is pi over 6. This is the answer that we're going to be looking for. And so here, the second 0 should occur at 3 pi over 2 in our first lap. All right, so we'll go 3 theta, because that is the term here, and set that equal to the second time we hit a 0 on the unit circle. Divide both sides by 3. We should get theta equals to 3 pi over 6, which if you simplify out equals pi over 2 and represents that point. So that is our second 0. Let's move on to the third point here, which will represent the first value on our second round. And so now we'll go 3 theta equals 5 pi divided by 2. Divide both sides by 3, or multiply both sides by 1/3, whichever is easier to kind of think about here. All right, and so those will cancel, and we'll get theta is equal to 5 pi divided by 6. So this value here represents 5 pi divided by 6. So now we'll write 5 pi divided by 6. That's our third value. What we'll do over here is we'll go on our second lap, our fourth term, and say, when does 3 theta equal 7 pi divided by 2? Well, let's multiply both sides by 1/3. Those will cancel, and theta will equal 7 pi over 6. That'll represent that value. So that's the fourth time that we cross the x-axis. What we'll do here, I can kind of see what that is, but let's just go on our third lap, and let's just say 3 theta equals 9 pi over 2. Divide both sides by 3, get theta equals 9 pi over 6. Simplify that out. We'll see that that equals 3 pi over 2. That'll be our fifth term, 3 pi over 2. And then we'll have one more 0 to locate here. So we'll go 3 theta, 11 pi over 2. 3 theta equals 11 pi over 2. And again, this is our third time around the unit circle, which we're doing because there is 3 complete cycles from 0 to 2 pi. We'll divide both sides by 3, and we'll see that the theta value here is equal to 11 pi divided by 6. 11 pi divided by 6 is the sixth term, and these are all the zeros that are represented by the cosine function, or the radian values of when this cosine function is equal to 0. So to finish off, let's talk about sketching cosine functions. All right, so here I have an amplitude of a cosine function equal to 1, and the number of cycles from 0 to 2 pi equals 2. All right, and so what I'm going to do here is I'm going to just pick some really convenient values. All right, so normally what I do is I go, all right, if I know it's 2 cycles from 0 to 2 pi, and I'm going from negative 2 pi to 2 pi, I know that the period is equal to 2 pi divided by the number of cycles, so it's just equal to pi. And so I'm going to make indication marks at every pi. So that way there's a lot of pi. And I like pie, especially apple pie. Oh, that sounds so good. I hope it's not lunchtime. And so when we're looking at this and we're trying to figure this out, the maximum is just 1. So let's just pick this as 1. This is -1. This is just a pretty standard cosine function. And now the thing to take into consideration with the cosine function that isn't the case with the sine function is you always start at the maximum. So we're going to go maximum. The minimum should happen in between and then back up here. So I'm going to go down, up, down in the middle between the two, back up. Let's go down, top it off at pi. And this is really what I'll be paying the most attention to is, are your minimums in between the periods and are your maximums appropriately placed? Turn it back around, back down, because that's what I consider most important at this point. And this is how you sketch a basic cosine function from negative pi to 2 pi of y equals cosine of 2x. So now let's flip it around a little bit. Here now we have an amplitude equal to -3, but the b value is equal to 1. So that means your period is equal to 2 pi over 1, or just 2 pi. And so what I'm going to do here is I'm just going to go -2 pi and 2 pi. But I am going to go 1, 2, 3, and go 3, and -1, 2, 3, -3, and identify those. And one thing I want to point out here is that there is a negative sign here. And if your function starts with a negative, you have to flip it across the x-axis. So instead of starting at the maximum +3 point, you have to start at the -3 point. You'll reach your maximum in the middle of the period, and then you'll end up back down here. Middle of the period, you hit your maximum, come back down here. So I'm going to draw out this cosine function. Woo. All right, and we'll go up, max, down, finish. And we just sketched the cosine function of y equals -3 cosine of x from -2 pi to 2 pi. So hopefully pretty simple and straightforward. Third example, let's look at a specific situation where we want to sketch from an interval of 0 to 2 pi for a cosine function that has an amplitude of pi and a period equal to 2. So that means your accelerating value, 2 pi divided by 2, this is equal to pi. So there's a pi number of cycles. There's 3.14 cycles from 0 to 2 pi. All right. And now since the period is 2, that's what I'm going to use for my tick marks here. So 2, 4, 6. But know that pi is about here and 2 pi is about there. But these are the tick marks I'm really interested in here because those are the ones that are separating the number of periods or the cycles that represent this function. So I see b is equal to pi, a is equal to pi, so this function is y equals pi cosine of pi theta. And so now what I'm going to do is that, you know, let's say this is 1 and this is -1, and we're going to sketch this thing out from 0 to 2 pi, right? Let's just assume a is greater than 0, so we'll start at the maximum. So we'll go down, reach a minimum here, back up, down, back up, down, back up, down, and so we'll go down, curve up, and then finish off, and we can stop about there. But this would represent this specific cosine function. So just some different examples to look at. It doesn't have to end at right here where the cycle is complete because we have 1, 2, 3, and a little bit extra. cycles in this specific cosine function from 0 to 2 pi. So with that said, I hope you have a little bit better understanding of how the unit circle applies to the cosine function, how we can go and look for specific radian values of a cosine function when it crosses the x-axis, and then also how to go and sketch some of these cosine functions so that you can apply the same aspects of sine functions to cosine functions. With that said, let's do some math.